Assalamualaikum warahmatullahi wabarakatuh. I'm from Group 5. Would like to present bar model using uncooked spaghetti in the shape of circle. In the mechanics of material, when a structure beam is loaded, it experiences external bending stress. These stresses change across the beam, creating tension on one side and compression on other side. For our project, Group 5 was assigned a circular cross section with a required thickness 0.5 cm and the length 30 cm. The great thing about a circle is has a perfect symmetry. This means its geometry resistant to bending, known as the area moment of inertia. It's actually the same in all directions. We calculate this using the formula inertia, which is next. Let's take a look at the main objective of our project. First, our academic goal is to apply core engineering theory in real life. We want to test how our spaghetti beam actually handle bending stress when real weight is applied. Second, we are required to analyze the internal force. We will draw the shear force and bending moment diagram for every single load we test. Finally, we want to calculate structural safety. By finding the exact point where the bar breaks, we can determine the allowable normal stress using the required safety factor of 1.5.
So we use bottles, uncooked pasta, scissors, rope, ruler, sellotape, electronic balance, and also papers. So for the fabrication method, the first step is to make a hollow circular mold with a diameter of 1.5 cm was fabricated using paper and sellotape. Then, the mold was left open at both the top and bottom to allow spaghetti strands to be inserted through it. Third, two mold sections were placed at both ends of the bar to maintain the circular cross-sectional shape of the spaghetti bundle throughout the fabrication process. Fourth, spaghetti strands were fed into the mold sections until the desired bar size was achieved. Fifth, additional sellotape was wrapped around the mold sections to prevent them from splitting open due to the large number of spaghetti strands packed inside. Then, sellotapes were then tightly secured around both ends of the spaghetti bundle to hold the strands in place and prevent them from slipping out. Last but not least, the finished spaghetti bar was inspected to confirm that the cross-section remained approximately circular and that the overall length complied with the project specification prior to testing.
How can I explain myself?
Louisiana shit. Murder on the beat. Something gotta cut up to you. Yeah.
First, we will start testing the bar with 500 grams of load. Next, we will test the bar with 1 kilogram of load. Then, we will test the bar with 1.5 kilogram of load. After that, we will test the bar with 2 kg of lead.
We're going to explain about the topic of the shear, bending moment, and their own diagram. Okay, from this page, we can solve that from the left outwards. We know that the total distance of the spaghetti is 30 centimeter. For each of the part of the spaghetti, they have 50 centimeter. So now we will took the data from the previous page. Here is the M1 and W1 there. The mass and the y of the each data are already listed at the left. So now we will take the data one first. M1 and W1. M1 is 0.5 kilogram and W1 is 4.905 newtons. So from here the calculation we can get that the force of the point A is 2.4525 newtons, and the force of the B is also 2.4525 newtons. So after we get the form from point A and point B, then we will do the shear force and their diagram. So at the shear, we find the shear force first. So we can get that V1 is 2.4525 newtons, V2 is negative 2.4525 newton, and V3 is 0 newton. After we will get this all the data, then we will draw the diagram that I have drawn it from at the right downwards. So look at the left. We already calculate all the bending moment. From our calculation, we know that the M1 is 0.367875 Newton meter and M2 is 0 Newton meter. Based on this bending moment, we draw it as a diagram like I already draw at the below. Here is the bending moment diagram that I have draw it like below. Okay. Now after that, we try to do the calculation of the data 2. So from data 2, we know that the y is 9.8y. So based on this, we calculate the force of point A and force of point B. So we know that the force of point A is 4.905 newton, and force of point B also is 4.905 newton at the right. So after we calculate the force of point A and point B, then now we'll do the shear force in the data 2. So on this shear force, we know that the V1 is 4.905 and V2 is negative 4.05 from the calculation at the right. So the V, we know that here is the we look the left outwards. We know that the V3 is 0 Newton. So based on the V1, V2, and V3, we draw the shear force diagram. Now here is the shear force diagram at the left downwards. Okay, so after we calculate the shear force and draw its own diagram, now we calculate the bending moment of theta 2. So to calculate the bending moment of theta 2, we see the left downwards, and here is the bending moment that I already calculate. So we know that the N1 is 0.73575, and look at the right outwards, and M2 is 0. Based on this all the bending moment, then we draw the bending moment of the diagram here, and here is the bending moment diagram that we have already drawn at the right. So after we complete the data 2, now we start to do the data 3. Before find the shear force, we need to find the force of point A and point B in data 3. So to find the force of point A and point B, we already calculate it, and then we see that at the right downward. So at the right downward, we know that the force of point A is 7.3575, and the force of point B is 7.3575. So to find the shear force, to find the shear force, we can see that the left that I have already calculated. So we can know that the V1 is 7.3575, V2 is negative 7.3575, and the last V3 is 0. Okay, so based on this shear force, we'll draw a shear force diagram that I have already drawn at the left downward. So we can know that the shear force downward, the maximum of shear force is 7.3575 and the minimum of shear force is negative 7.3575. So now after find the shear force and draw their own diagram. So now we find the bending moment in data tree. So to find the bending moment of data tree, we need to apply a formula. So we can see at the right that I have already calculated. So first the N1 is 1.103625 and N2 is 0. Okay, so based on this bending moment of the data, so we can know that the maximum of bending moment is 1.103625. So based on this, then we draw the bending moment diagram at the right below that I already calculate. Okay, so here is the bending moment diagram in data tree. Okay, now we end here. So we go to the last page. It also is the first. So from the data flow, we know that the Y of the W4 is 19.62 Newton. So based on this, we'll try to find the force of point A and point B in data flow. So we look the left. So from the left, we know that the force of point A is 9.81 Newton and force of point B also 9.81 Newton. Also based on this, so we get the force of point A, point B, force of point B, and also the Y. So based on these three, we try to calculate the shear force in data flow. So look at the left below. So from the left below, we know that the V1 is 9.81 Newton, V2 is negative 9.81 Newton, and V3 is 0. So after that, we will try find the bending moment in data force. So to find the bending moments, so look at the right. So we know that the M1 is 1.4715 Newton meter and M2 is 0 Newton meter after the calculation. So we already find the shear force and bending moment in data flow. Now we based on this to draw the shear force and bending moment diagram. So here is the below of the shear force and bending moment of diagram in 4. So we can see that in shear force, we know the maximum of shear force is 9.81 Newton and the minimum of shear force is negative 9.81 Newton and the maximum of the bending moment is 1.4715 Newton meter. Okay, that's all.
First, we designed a constructed composite spaghetti bar with a length of 20 cm and square cross section by 1.5 cm. During this bending test, the bar showed elastic deformation before it finally failed, which means it's bent gradually before breaking. The maximum load that the bar was able to support was 2 kg, which is equivalent to 19.62 newtons. After applying a safety factors of 1.5, we determine the allowable stress to ensure the design can be used safely within its loads limits that we showed before. Overall, our experimental results were consistent with the theoretical concept of bending, internal stress, and structural failure. We also found that the cross-section area plays an important role in determining the load-carrying capability of the structural member. Next, I would like to share our reflection of this project. This project helped us gain a better understanding of bending behavior and structural analysis through practical testing. We learned how to apply the engineering theories that we studied in class to a real experimental by designing, constructing, and testing a composite spaghetti bar with uncooked spaghetti. Through the project, we also improved our problem solving, teamwork, communication skill, especially when facing challenge during the fabrication and testing process. Overall, this project provides us with a value practical experience and strengthens our understanding of structural engineering concept. That's all from us. Thank you.